Thank you. Thank you all for coming. Good afternoon, and thank you for the kind invitation. It's a pleasure to speak in front of you today. So we're going to shift gears. I'm afraid those of you who are tuning for mathematical rigor are going to be disappointed by the talk. And we're going to also change topic. It's going to be about active swimmers. And I recently moved to the UK, to Loughborough University. I'm part of a new group, the Interdisciplinary Center for Mathematical Modeling at Loughborough University. And today, well, I want to tell you a couple of stories, but first, let me tell you about the heroes of the stories, the people with whom today I will just have white slides, empty slides. The heroes are Rebecca Breier and Fabian Schwarzendahl, two PhD students working with me. Now, both of them are doctors, and they performed the main work I'm going to discuss today, and also acknowledge the wonderful collaboration with Christian Alescu and Michel Wilczek. All of them are the Max Planck Institute for Dynamics and Self-Organization in Göttingen, was my previous institution. I also acknowledge the collaboration and help of Stefan Emminghaus and Oliver Boimschen. Those are the funding agencies and the institutes involved. All right, so I want to tell you two stories. Ideally, probably there will be only time for the first one, which is about the emergence of phytoplankton patchiness in mild turbulence. If there is time, I'm going to tell you about something about a general result in simulations, the analytical theory about density heterogeneities in active swimmers. All right, let's push on. So first I want to tell you about a very impressionistic view of what is the life, the typical life of a micro swimmer. So if you think that your life, your day was tough, think again, because the life of a micro swimmer is much, much tougher. So these small creatures, they live in a very complex environment. They're all competing with each other for light, for nutrients, for oxygen or minerals. They are secreting different biochemical signaling molecules. They are eating each other. They're trying to mate, and so on and so forth. They live in a very heterogeneous environment, heterogeneous from the point of view of the biology, the chemistry, and also the physics. They're subject to lots of shear stresses, hydrodynamic interactions, and so on and so forth. So in this general landscape, we try to do some modeling to try to capture some key elements to describe what's happening. And I want to tell you about phytoplankton. So phytoplankton, phyto is the Greek stem for plants. So these are really, microscopic plants. And perhaps you've been lucky enough to see a picture like this in some exotic location. This is a phenomenon of bioluminescence of planktonic cells. So these are, microscopic creatures in the micron-length scale, and there is a myriad of different species. A marine biologist, taking a bucket of seawater, is bound to discover new species. Actually, we still, only know a few. Many, but a fraction of what's out there. They are plants, so they have chlorophyll. They use it to produce energy using solar light, sunlight to produce energy. They're also responsible, just a note, for at least 50% of the oxygen that we breathe. So they're extremely important. They're the base of the food chain in oceans and seas. So they're incredibly important. Sometimes, if in lakes or oceans the conditions are right, a phenomenon called algal bloom will emerge. So this bright green that you see here, so this is a satellite picture. This is the Lake Erie between US and Canada. What you see is an algal bloom. The conditions are just right so that these creatures start multiplying enormously, and they form algal blooms. So what you see is these structures are highly heterogeneous. These streaks are highly dense portions of water, highly populated by plankton. Here inside there is much less. So algal blooms has been known for really millennia. Sailors have known for millennia about algal blooms, sometimes coloring the seas of red or bright green. And these are on this scale. These algal blooms, occur on the scale of kilometers, hundreds of kilometers. and also on a global scale. And unfortunately, recent data tell us that because of climate change, the diversity of plankton, phytoplankton, plankton in general, is decreasing. And that is really bad news because phytoplankton produces oxygen, for example. Okay. The importance of plankton is being recognized more and more by the scientific community, by the marine biologists, and increasingly so also from the point of view of physics. Indeed, more recent data due to advances in technologies have shown that this patchiness, so the technical word used by marine biologists is patchiness, this heterogeneous distribution, very dense here, low density here. This patchiness extends not just at the kilometer scale, but goes down to the meter and sub-meter scale. Okay? So these are some data. Believe me, if you cannot see it, for example, you can measure the chlorophyll, and you see that there is variation at the sub-meter scale, down to the millimeter scale. Now, that's paradoxical, because any mild, stirring of water, you expect to homogenize this distribution of microorganisms. Think of pouring your milk in your coffee in the morning. You stir it with a spoon, and then it becomes homogeneous. At that scale, you imagine that even mild turbulence will homogenize it. Okay, so that's a paradox that needs to be explained. So that's what we did. We did some simple modeling. So this is a very simple-minded modeling. To paraphrase Dejean, is the poor man's model for phytoplankton. So we're going to have an equation governing the translation, the motion of these particles. So these are simple particles. So R is the position, this is the time derivative. The change in position is due to the self-repulsion. These are motile particles. Not all phytoplankton, by the way, is motile, but 90% of the known species, the species known to create harmful algal blooms, are motile. So there is an interest in motile phytoplankton. There is also advection due to the external field. These microorganisms swim in a fluid environment, and there will always be some even mild level of turbulence due to winds, to tidal currents, and so on. So that's the advection due to the external turbulent field. Then I need to tell you also, this is the equation governing the change of direction of motion. So E is my direction of motion. So the time derivative is due to a reorientation, and this is due to an interaction between different planktonic cells. So when two planktonic cells come close enough, they will interact hydrodynamically. So the motion of one planktonic cell will propagate through the fluid, the interstitial fluid, and influence the directional motion of the nearby cell. So this is, just to give you a gut feeling, is what happens when you go to the swimming pool and Michael Phelps, for example, is swimming next to you. You will feel the wavelets propagating to you, and they will perturb your motions. That's the hydrodynamic interaction. I'm going to tell you a little more about in a second. Then there's noise. There's always noise. Just because the fluid has a certain temperature. Well, also these are biological entities, so there is also an internal biological noise. And finally, the vorticity. Again, the external field will also change the direction of motion. The reorientation, the liquid crystal experts here recognize the level Lusher potential in spirit, at least. We're not working on a lattice, we're working off lattice. But basically, we know from hydrodynamics, the hydrodynamic fields generated by such active swimmers, to a very rough approximation, as this nematic symmetry. That means when two such swimming cells come close enough, they will tend to align either parallel or anti-parallel. Okay? The reality is a little more complicated, but this is a very rough approximation. Additionally, we calculate this interaction only up to a certain distance. Okay? So only within a sphere of neighbors. Great. I told you about an external field. We calculate the mildly turbulent external field in two ways. The first is called the Krachnan method, and again, is a poor man's turbulence. It's very simple, very fast computationally, and this is because it's just a simple Fourier sum of with some random vectors. But these random vectors are chosen such that they satisfy the Kolmogorov scaling. What you see here, k is the mode to the power minus 4/3. That's what you expect from the Kolmogorov scaling. We also use a second method to generate the turbulent field, and this is much more advanced. What we do, we take the full Navier-Stokes in the full glory, which you see here in the vorticity formulation. So omega is the vorticity field, and we solve them with direct numerical simulations, which means that you take your volume, your simulation domain, you discretize it with a simple grid, and you discretize the equation and you solve them brute force. Okay? Great. So we're going to use both Krachnan and turbulence because it's computationally very fast. Okay, allows us to explore the phase map, the phase diagram. But in some situations, we're going to also use direct numerical simulations, which are much slower, but also we trust them more to explore verify some statements and explore some states. Okay, I need to tell you also about scales and dimensionless numbers. So first of all, I've been talking about mild turbulence. Let's quantify that. So a typical way to quantify that is the Reynolds number. For people who are not familiar, that's another dimensionless number commonly used in hydrodynamics. It's the ratio between inertial forces and viscous forces. Okay. Now turbulence. If you know some works on turbulence, you know that people typically are interested in very, very large values of the Reynolds number. That's what you find in the atmosphere or in other conditions. Ecologically, however, if you make a measurement in the oceans, you're going to find a much lower value of Reynolds. So this is the Taylor-based Reynolds number, and that's about. We chose a value of 20. We tried, something a little larger as well, but we're going to stick to a value of 20. So ecologically, you're going to find Taylor-based Reynolds number of 20, 50, 80 are absolutely realistic. That's what you're going to measure in the oceans, and that's what we use. Then I need to tell you about the Peclet number, which is another dimensionless number. So our definition of Peclet is a reorientation of Peclet, and it's the ratio between two characteristic time scales. One is gamma. Gamma is an inverse time. Is the inverse time that takes for the orientation of these active swimmers to change due to the hydrodynamically mediated cell-cell interaction. So that's one time, and dr is just the rotational diffusivity. Okay? Then we're going to need another dimensionless number to compare two other interactions. Gamma, again, the same inverse time scale of reorientation, and omega k, which is the so-called Kolmogorov shear rate, and it is a time scale associated with the turbulent vortical motion. All right? So that's another ratio of two time scale, so that's a dimensionless numbers used to compare the cell-cell interactions and the turbulent, the characteristic time associated with turbulence. Now, phytoplankton there are gazillions of different species, but typically phytoplanktonic cells have sizes between 1 and 1,000 microns. Okay, that's what we know from marine biology. At the realistic Kolmogorov length scales set by the average dissipation, that's in the 100 of microns. Okay, so we need to include cell-cell interactions in the modeling of this active phytoplankton, and so that's what we did. All right, on with the results. So these are some results. So we take our externally, our externally generated turbulent field. We put our model for active phytoplankton, and we evolved that into this external field. Mind, we are in the regime of light phytoplankton in terms of mass. So the phytoplankton from motion will not feed back and influence the external turbulent motion. Okay? That is valid for the lighter species of phytoplankton. is absolutely not valid for larger creatures, zooplankton, so the things feeding on phytoplankton, for example. All right, so what you see, that's one simulation box, that's a zoom. You'll see there are some little clusters. Well, you trust me, what you should see are some arrows with some colors. The blue-violet scale gives you a measure of the local density. So you see there's some regions where dark blue, almost black, and other regions are completely empty. Okay, this is just a fraction, by the way, of the particles, otherwise too full to see anything. The reddish hue, that's instead a scale of the magnitude of the vorticity. So these elongated banana or croissant-shaped objects, those are the vertical core. That's what you expect from turbulence. It's well known that the vertical cores have the shape, they're a little elongated and a little bent, okay? Actually, our turbulence expert, Vilcek and Lalescu, were actually surprised to find the same shapes or this low value of Reynolds number. So for them, the turbulence experts, 20 is nothing, it's peanuts, is a kid's game, okay? They're used to Reynolds in the hundreds, in the thousands. All right, what we see is that there is patchiness, there is a heterogeneous distribution of the spatial distribution of these planktonic cells is heterogeneous. Well, we repeat the simulations for a number of state points. So these are another phase diagram. On the vertical axis, we have this Peclet number. On the horizontal axis, we have this the vertical Stokes number, which was the time scale, the ratio between the cell-cell interaction and the turbulent time scale. The color bar gives you a measure, a number associated with the patchiness. How do we do that? Well, effectively, we do a Voronoi tessellation of the system. Is everyone familiar with Voronoi tessellation? Yes? Wonderful. Then we just take, we take the top 5% of the densest Voronoi volumes, densities. We compare it with an equivalent distribution, but just for purely randomly distributed particle, and we divide it, we normalize that with the average density. That's our patchiness factor Q, which is what you see on the color bar. So anything larger than 0 tells you that you're above random, your signal to noise ratio is considerable. So what the take-home message of this slide is that you see you go from blue, relatively low values of patchiness to this golden color, and then again to blue. So there's a sweet spot for patchiness at some intermediate value of the vertical Stokes number. All right, let's try to understand that. Well, first let me show you a comparison to make sure that we're doing everything kosher. We compare the Kratchner turbulence, which was the computationally cheap, fast, but technique, but Kratchner turbulence misses some points, which is the non-Gaussian tails in the velocity increments distribution, for example. We're losing something. We're losing something in this computational cheapness. So we compare with the direct numerical simulation. Those are the blue squares. What you see here is a cut, a horizontal cut across this phase diagram. So we fix the Peclet number and we change the time scale ratio as omega, and what you see is the value of the patchiness factor. So the maximum corresponds to the sweet spot we just saw in the previous slides, and we compare the circle for Kratchner and the squares for DNS. You see the maximum fall more or less at the same value of the vertical Stokes number. We're also changing something else. We're studying both point-like particles, also extended particles. So with a finite size and short range repulsion, so the particles cannot interpenetrate. And again, the results are roughly, the peak falls in the same ballpark. The numbers for on the left scale, that's for extended particles, are much lower than the numbers on the right scale for point-like particle. That's because point-like particle can have no limit to concentration, while extended particle, of course, have some short range repulsion. All right, so there's a fairly good, at least qualitative agreement between DNS and Kratchner turbulence. All right, there is one more length scale I need to tell you, which is an integral length scale, which in practice is the characteristic size of these vertical regions. So even this mild level of turbulence will create some vertical regions which are typical of turbulence. So you can calculate a length scale associated with that by considering the following quantity. So it is standard practice in turbulence literature to take the velocity of the fluid at a certain position r and a time t, and then calculate the same quantity but at a position shifted, okay, at the same time, and then calculate a correlator of that. Okay, what we've done here, we're taking the vorticity, okay, because that is the important quantity for us. So we've taken the correlator of the vorticity at two different points in space, and that's our correlation function f omega, function of the displacement lambda. What you do then, you integrate over all the possible displacements, and that gives you a number with the dimensions of length. That's our integral length scale associated with vorticity, which is roughly the size of your vortex. The region, the size of the region affected by the vorticity. Okay, what we do is we change now the integral length scale, so this number, properly normalized, and we look at the maximum patchiness. So the maximum, the sweet spot I was showing you before, okay? So that's what you see on the vertical axis, this maximum, the height of this maximum, when we change integral length scale. We have changed a number of parameters, the average room mean square velocity, characteristic, the active, the self-propulsion, and other physical parameters. The take-home message is still the same, though the numbers are a bit different. The take-home message is that as the region affected by this coherent vertical motion increases, the amount of patchiness in your system will increase. Indeed, let's go back to something that I didn't really highlight before, no one asked. When we use this curly L, is the same quantity that I just showed you, this integral length scale, properly normalized, then the patchiness tells the sweet spot of patchiness falls between 1 and 10. So that tells us that perhaps we have caught the cat by the tail. Perhaps this tells us that when there is a balance between the length scales or the time scales associated with the turbulent motion, even in these mild conditions, and there is a balance, between that the length scale associated with that motion and the interaction distance, the typical interaction distance between this active motion, then a maximum patchiness emerges. So these are the initial conditions leading to perhaps a runaway growth that can lead perhaps to an algal bloom. Of course, or in that situation, other interactions, also biological interaction, which we neglect here, will start to play a role. All right, that's a pretty movie from our simulation, though not much is visible because these are very subtle correlations. But there is a saying that soft matter physicists just like to show pretty movies. So with this movie, I've satisfied my requirements. All right, so I've reached the conclusion list of the first part, in that mild turbulence can lead to small-scale patchiness in a model of phytoplankton. High values of turbulence, as you see, eventually the sweet spot dies away. So high values of turbulence actually destroys patchiness, homogenize, like at one point you would expect. Think again of milk in your coffee. And when the length scale associated with turbulence roughly matches the size of the cell-cell interactions, strong patchiness emerges. All right, how am I doing with time? I still have another 5-10 minutes?
Yeah, go for 13 minutes.
13, so perhaps, unless there are questions, now it's a good time to ask me a question about the first part. Yes, please.
What is the meaning precisely of the term cell-cell interaction?
It's the hydrodynamic mediated interaction.
Hydrodynamic mediated.
Yes.
So it is not said by charge.
No,
dipole,
absolutely.
Nothing.
No chemistry. We are neglecting chemistry. We're neglecting any biological interaction like worm sensing. It's absolutely hydrodynamic interactions. So the example of the swimming pool I made earlier.
Right. Why is it up-down symmetric?
That just turns out to be the symmetry of this, the flow field generated by an active swimmer. So it's not as a nematic symmetry. Okay, because think of it, because an active swimmer is a force-free object, okay? So at the minimum level can be described by two equal and opposite forces. Okay? So this will generate a flow field with quadrupolar symmetry. Okay? Hence the Natl symmetry. Yes? Happy? Everyone happy? All right. Then let me give you a list of glimpse. Oh, here we go. Here's the answer left to your question. It was in this picture. Let me give you in the few remaining minutes a glimpse of what the second part of this are. So I want to talk again still about biological microswimmers, and for these small creatures here I have two examples. Common model organism studied by scientists. One is Chlamydomonas. So this again is a plant, is a microplant, is an alga. Has two flagella in the front, it moves the flagella in this breaststroke motion. In this way it propels forward. The other example is E. coli, Escherichia coli. It's a pusher, it's got many flagella, and they form a bundle and they propel the cell forward, so the bundle is in the back of the body, and in this way it propels itself forward. So Chlamydomonas is a typical example of a puller, okay, because it pulls fluid from the front. So this is a sketch of a Chlamydomonas. These are two flagella. It will pull fluid from the front, and fluid will also be pulled from the back, and then will be ejected from the sides. Pushers like E. coli do the opposite. You see the arrows are the same, just flipped around. The E. coli will push fluid in from the front and in the back, okay? And you see, as I just said, these at the minimal level, you can describe this by two equal and opposite forces. There's just two ways of arranging that, okay? So the question we want to address is, what is the influence of hydrodynamic flow on the collective behavior of such swimmers? So we developed, together with Fabian, we developed a model for microswimmers. So this is a sketch, an artistic sketch, the artist being Fabian and myself, of Chlamydomonas. What you see is the cell body, the two flagella. We don't explicitly model the flagella. What we do instead, we replace the flagella by another sphere, larger, which represents the regional space spanned by the motion of the flagella. Okay? So our model is effectively an asymmetric dumbbell, okay? Two unequal spheres. It's rigid. The red spheres instead, this is the location where we apply the forces. Okay, the two forces I was showing a moment ago, these light gray arrows. Now we know from careful experiments by Drescher and collaborators that in an appropriate way to model the motion, the flow field generated by Chlamydomonas is actually using 3 force points. Now the total sum is still 0. So these two red spheres in the front are a bit smaller, but their sum is equal and opposite to this one in the back. E. coli is simple. E. coli is just a force dipole. Okay, that's a model for E. coli. We do rigid body dynamics with quaternion. I think I can skip this. We fine-tune the model. Obviously, there are many numbers in the model. The sizes, the characteristic sizes, characteristic speeds, relaxation times, when these objects interact with the other, in collision with walls and so on. We fine-tune this with, the nice experiments of Tanya Stapenko and also the Max Planck Institute, working with the group of Oliver Boimschen. So we fine-tune that. So this again, the asymmetric dumbbell model. So we were able to have pretty good agreement with simulation experiments in these different set of experiments. I'm not talking about this today, but I just want you to appreciate the goodness of the agreement. So that's, at least for Chlamydomonas, that's what we do. Either take numbers from our own experiments or known from the literature. The fluid. We model here the fluid explicitly with a technique called multi-particle collision dynamics, also called SRD, different flavors of the same thing. I don't think I have the time to tell you about this, but please ask me questions, okay, if you're interested. But briefly, it's an explicit method, also computationally cheap, to model a fluid, including hydrodynamic interactions. Okay, so armed with this computational technology, we start our simulation. So this is our simulation box, 3D, periodic boundary conditions everywhere. These are our little Chlamydomonas. That's the initial configuration. We just throw them randomly in our domain. after some time, well, some days really, we have a final configuration. What you see, the some holes open here, okay? So this, if there is this low density region, means that somewhere else the chlamydomonas have gone to a little denser configuration, okay? So again, a little bit of patchiness, density heterogeneity, heterogeneous spatial distribution of these swimmers. When we quantify that, okay, this is the validation, I can skip it. We quantify that again with a Voronoi analysis of the distribution of the swimmers. In this case, we look at a simpler quantity, which is the standard deviation of the Voronoi distribution of volumes. And as a function of time during the simulation, we see that this distribution is probably normalized with the random distribution, okay? So starting from 1, after some time, this grows with time. So heterogeneous distribution, the distribution grows more and more heterogeneous. And we repeat this for different filling fraction, the main result is the same. We repeat this again for different Peclet numbers and different filling fractions in our domain. This is our phase diagram. The color bar is again a measure of this heterogeneous distribution. Again, the bright yellow tells us where it's larger, and there is a large region where it's larger. And again, there is a maximum here. Okay, so we can, if you fix the Peclet number, you change the filling fraction, you're gonna see a maximum in the density heterogeneities. So this again, our horizontal cross-section across the previous phase diagram. So we fix the Peclet number, we're changing filling fraction. The data I showed you a second ago are here in these green circles. Now we do two things, because in the computer you can do pretty much everything. You can switch off, for example, the steric interactions and have only hydrodynamics interactions. So interactions mediated by the fluid. Those are the square orange symbols. You see here that the heterogeneities grow much stronger as a function of filling fraction, okay? And then we do the opposite game. We kill completely hydrodynamics and we only have steric interactions. So effectively we have, without effector, we do have an active Brownian particle system, okay? No fluid, just activities on propulsion and some lingering noise. Those are the blue triangles here. So there's no maximum. Now this already points us to a conclusion, which is corroborated by the analytics that come in a second, that this maximum might be a consequence of an interplay between hydrodynamic interactions and steric interactions. Let me run through the theory very quickly. So we start from a Phytoplankton equation, and we take an ansatz which is actually common in the literature. We take the velocity of our swimmers, a function of the concentration, okay? And we do the simplest ansatz is a constant minus the concentration times a coupling zeta. Is not in the literature. So we start with the Phytoplankton equation. We project it in the moments, the 0th moment for the density, the first for polarization, and the second for the nematic tensor. From the Phytoplankton equation, you derive equations for these moments. You linearize, you go through space, you linearize, and what you have, this is the final result. The equations are horrible. All right, for pullers, where this F is negative, F is the strength of the active motion, we find that there are two important terms conveniently boxed here. This one is unstable term, depends on F. That means that an initial fluctuation, delta, in the concentration will grow in time, leads an instability, so growth of fluctuations in concentrations. However, there is a higher order here, a C naught squares. You see, this term is proportional to C naught. This term is proportional to C naught squared. So a little higher term in the background concentration. There is a stabilizing term as the opposite sign. Okay? So this will bring down the instability. So, conclusion that this analytics, this linear stability analysis, tells us that there is a competition between hydrodynamics and steric interactions, and this gives rise to a maximum. Indeed, if you plug realistic numbers for Plurus chlamydomonas, you find a maximum around 0.12, which is in the ballpark of what we find, a very large ballpark, like Fenway Park in Boston. Okay, so we do the same for For pusher, go back. For pusher is the same, at least in spirit. Details are a little more complicated. Here, the core of the instability emerges from the band fluctuation of the nematic tensor. By GAN, the golden square here tells you that there is an instability still due to hydrodynamics, while at high order, in the background concentration, there is a stabilizing term due to the steric coupling. Okay? So the conclusion is still the same. Here, for realistic numbers, we get a maximum around 0.2, roughly in the ballpark of the simulations. Well, this is just a summary of what I just said. So I reached my conclusions. So if you measure the heterogeneous distribution of swimmers, we find that there is a competition between hydrodynamic interaction that leads to an instability and steric interaction that eventually stabilize that instability, kill off the instability. Thank you for your attention.
Questions?
So that filling fraction, why do you stop at 0.3? Is there some reason or it's computational?
Always becomes increasingly more difficult.
But we have an idea what happens.
We expect this heterogeneous, heterogeneous distribution to decrease. Yes.
And also in the
I don't know.
one that you were showing before when we were comparing, just switching the hydrodynamic interactions and so on.
I don't expect anything new to emerge there, but perhaps we should build a larger collider.
So in terms of breathing in the future, how serious is this?
Oh, that's really bad news, actually, if you ask me, because as I was mentioning briefly, climate change is killing the diversity of species of phytoplankton. And cyanobacteria, for example, are responsible for the oxygen. They created one of the first global catastrophe in the history of this planet, because before there was no oxygen, then suddenly there was this oxidizing element, but then eventually life evolved to use it. And you start, do something to the environment that destroys a species we may not even be aware of, and we don't know what happens when we kill them off. So it's really bad news.
I'm sorry, are you saying they cause global warming?
No, the opposite. We cause global warming.
But
The
they
plant,
made they made all the
cyanobacteria produces oxygen, which we breathe.
Right, so it's their fault.
This is recorded, so we should be careful what we
Oh,
say.
okay.
Some
Alright, it's not
people
their
might not
fault.
have our sense of humor.
Okay, sorry.
Now, global warming is anthropogenic, as we know, and we are destroying our environment.
Pessimistic news, maybe. Other questions? Okay, thanks again.